I hope you're able to see me now,
Yes. Yeah. Yes. Wanting to. In a few minutes, we'll start. Start பண்ணிடலாமா? Can we start? Okay.
Shall I start now? Good evening to all. I welcome you all for today's webinar topic on Bihan GPU application specific ICC in AI research and deep learning. I invite Mr. HR Mohan, Chair Events IEEE CS Madras, to give welcome address and introduce our speaker. I welcome you, sir.
Greetings and good evening to one and all. On behalf of the organizing units, IEEE Computer Society of India, ACM, and IEEE Circuits and Systems Society, I have great pleasure in extending a warm welcome to our today's speaker, Mr. Rajeev, the members and colleagues from the organizing units, and the delegates joined the program through Google Meet, and those watching the event on YouTube streaming. GPUs developed mainly for gaming applications have become extremely popular for AI applications after the launch of ChatGPT in 2022. It may not be out of context to talk about the company NVIDIA, which was focusing on GPUs, had seen unprecedented growth in its market valuation from 2022 and has become the most valued company in the world with $4.5 trillion, surpassing the well-known tech companies Microsoft and Apple. One point of time, it had funds just adequate to run the company for 1 month. And over and above, the GPs have become so valuable that American, US, they they banned the export of GPUs to countries like China and few other countries who are competing with the US in AI research. So our presentation today is on beyond GPUs, application-specific ICs in AI research and deep learning. For more than a decade, GPUs have dominated the landscape of deep learning, training, and inference. Their highly parallel architecture, optimized for matrix operation, has enabled the rapid growth of AI research and applications. However, as models grow larger and workloads become more specialized, a one-size-fits-all approach is no longer adequate. This is where the application-specific integrated circuits is popularly known as ASICs, such as Intel, Habana, Gaudi, enter the scene. ASICs belong to a broader category called domain-specific architectures. Unlike general-purpose processor, DSAs are custom built for unique requirements of a particular domain. In the case of Gaudi, the domain is deep learning. Yeah. By focusing on the computation and memory access patterns of AI workloads, Gaudi delivers higher performance per watt, better scalability, and lower total cost of ownership compared to general purpose GPUs. Intel Havana Gaudi processors, for instance, are architected to accelerate both training and inference. They integrate dedicated hardware blocks for matrix multiplication, on-chip high bandwidth memory access, and optimized interconnect for large-scale distributed training. These design choices address two of the biggest challenges in AI infrastructure today: memory bottlenecks and inter-device communication overheads. The emergence of ASICs doesn't mean the decline of GPUs. Instead, it represents the diversification of the AI hardware ecosystem. Just as CPUs, GPUs, FPGAs, and DSAs coexist, the future of AI will increasingly rely on heterogeneous compute environments where the right hardware is matched to the right workload. In summary, domain-specific ASICs bring efficiency, scalability, and cost-effectiveness to AI research and deep learning. By tailoring hardware to the specific characteristics of AI workloads, they ensure that as models grow in size and complexity, the infrastructure supporting them remains sustainable, performant, and purpose-built. Now, let me have the pleasure of formally introducing the speaker, Mr. Rajeev from TCS Kochi. He is not new to us. He has delivered a presentation on machine learning beyond algorithms in November 2022 and has contributed several articles for the IEEE India Council newsletter. Mr. Rajeev brings over 25 years of IT experience with more than 10 years dedicated to artificial intelligence, machine learning, and deep learning. He has worked with multiple Fortune 100 companies, delivering over 10 impactful projects across domains like banking, insurance, and semiconductors, with exposure to life sciences, retail, and utilities. Throughout his career, Mr. Rajeev has played roles from developer to chief architect, authored more than 25 technical papers, filed 6 patents, with few have been already awarded, and participated in over 5 boards of studies. He has actively contributed to shaping academic curricula in line with the industry needs, while mentoring students and guiding interns through real-world projects. His initiatives include faculty development programs, train-the-trainer sessions, and technical mentorship to bridge the academia-industry gap. Mr. Rajeev has delivered more than 50 talks across industry and academic forums, served as a judge in various competitions, and was finalist in the prestigious Tata Business Leadership Award. Founding member of AI Saturday Kochi, he is closely associated with IEEE, KMUG, and industry bodies like NASCOM and KESA. His passion for innovation, thought leadership, and mentorship continues to make a lasting impact both in technology ecosystem and in academia. With these briefings on the topic and the speaker, let me invite Mr. Rajeev to take over the session and enlighten our participants on application-specific ICs in AI research and deep learning. Over to Mr. Rajeev.
Yeah, thank you. Thank you, sir, for the, that introduction. So let me share my screen and please let me know once you are able to see it so that I can continue with the presentation,
Yeah, visible.
Okay. Yeah, thank you. So today we are going to get into an ASIC from Intel called, basically called Gaudi. So before we get into that, what is the problem that today typically we are facing? So the amount of compute requirements are constantly increasing, which means that the power consumption is increasing. And if you see data centers from kilowatts to megawatts to even gigawatts, we are talking. If you have read that recent Microsoft, some of the data centers, they are talking 5 gigawatts. 5 gigawatts is huge power. You can think about what type of heat it generates, what type of cooling it needs. And many of some of the accelerators in the GPU, latest ones, do not even work with air cooling, water cooling. They need actually what is called immersion cooling. So the question comes is, what can be done in software architecture that allows the power consumption to be less, the heat generation to be less, and the total cost of ownership? And that's where domain-specific architectures comes into picture, because the entire field, basically the DSA is a broader term actually, and application-specific. So the Gaudi is predominantly designed for deep learning workloads. So it can run LLMs, it can run traditional convolutional neural networks type of things, or even things like image generation and stuff per se. So they are designed for that. Now, before we get into the core of it, there are so many different architectures. If you see here, key differences and stuff. I'm not going to go deeper into each of them, but it's not that one architecture dominates over another. Each of them have its own purpose. CPUs are still a lot used, but they have certain limitations per se. GPUs are there all over the place, you can see. And then, accelerated processing units, which is basically combining different processors like CPU, GPU, and NPU. So if you know the Meteor Lake or the Lunar Lake laptops that you see from Intel today, they come with 3 processors actually. So they come with CPU, they have a GPU, and they have an NPU in them, So it is basically taking advantage of all the 3 processors in that system that's there. So the last you see, tensor processing unit, that is actually classified under the ASIC actually. So that's from the Google, but today what we will see is the one from the Intel side of it. There are many more companies who are making it. So we will not be going into each of them, their specific advantages and disadvantages. But overall, you should understand that there are different hardware architectures available there, depending on the problem, size, many other parameters. We decide what should be chosen and what should not be chosen, per se actually. Now, moving on, the question comes is there something new coming up? Obviously, there are many new things coming up. So you can see the top one is the ASICs that we have discussed. So today, there are many more players. As if you see Cerebrus, Wafer Scale, Grok, Tensor Torrents, Samba Nova, and TPU I introduced. Then Intel Gaudi is there. Then you have AWS has Inferentia and Trainium. So quite a few of them which are coming, beyond the GPUs. And we'll go into a little more detail as to what it is there. But what I want to highlight in this slide is that even there are some new paradigms that are coming up, like photonic chips, because Mohan discussed about matrix multiplication. The question comes is, can we move from electronics to photonics for doing something like that? So there are processors today available, but they are not as powerful as what we need. But these type of things can change in a decade's time, and obviously you all know that whenever you do between electrons to photons, the amount of heat comes down and the processing speed increases. So typically you can do much higher computation with photonics than electronics, with probably 100th or less than that of the heat and power consumption. So that way it is very, very important. And then neuromorphic, analog, there are quite a few processors in the analog space. Quantum is something which is coming. Then there are other very specialized, like probabilistic processors and stuff. So with this basic background, now we are going to get into little more detail into Gaudi. So first of all, why an ASIC? Obviously, many of the customers who are using needs more choice. If you see, sometimes GPUs are very difficult to get. Added to that, even if you get it, they are costly also, because each instance, whether you buy it or you take it from cloud, it doesn't matter. Actually, there's a cost associated to that, and sometimes the cost is not, it doesn't come cheap actually. So if you have heard the government purchasing GPUs for $5 billion, you can think around 36,000 or something like that. It's in the 30 to 40,000 range. So you can think what each card costs. So almost you are spending like 40,000 crores for approximately 40,000 cards type of a thing. In which case probably you are paying like 1 crore for a card type of a thing. Yeah, that is the type of cost we are talking about. This is why many colleges do not have like large scale clusters and stuff, which is very difficult, because there's quite a few investment required to get this working. Then lock-in technology. See, if you see something like NVIDIA, they use CUDA. There are many things in the NVLink in the architecture, both hardware and the software side, which are actually proprietary to NVIDIA. So Intel wanted to change certain things here. So in the case of networking and stuff, they are using more open architectures where you are not charged for the licenses. So one thing you should understand is that when you get enterprise licenses, beyond the hardware cost, you are paying for the cost of the license also. Then ability to scale, which anyway GPUs can do. I want to build a cluster of 1024 nodes. Yes, it can also scale per se. Then maximize efficiency, as I said, both in terms of power consumption, which in turn relates to the cost per se. So these are, I'm not going to go through read this, but some comparison has been done with respect to NVIDIA in this case. And then it discusses for each of the 4 points we discussed, how it differentiates from a Gaudi perspective. Now the question comes is, what type of applications do I? Because that was I saw that in one of the questions also. It is there. So obviously, that there are different modalities when we are dealing with text. It could be traditional LLMs, which are large language models, which allows us to do things like summarization, which allows us to do information extraction, which allows us to build chatbots on a set of documents. So more like RAG, retrieval augmented generation systems, where you ingest the knowledge and then you query that knowledge basically for anything very dynamically, or video generation, audio generation. So there are quite a few deep learning use cases where these accelerators are used, both for inference time and the training time, because both are two different functions. So the training necessities are different, because in training you talk about large clusters and stuff where you can train a model, whereas inference is more of a horizontally scaling application per se. So the multimodality is a case where you basically combine text plus image. So I will just give you an example. So if you were to upload an image and then ask questions on that image, or you upload an image and then extract the contents of it, more like an OCR, optical character recognition technology type of a thing. So most of these uses either transformer-based architectures or traditional convolutional neural network architectures or different type of architectures, and then there are embedding models where you can embed an information into a vector space, So whether I embed text or whether I embed an image, I can convert them into either a 512, vector, or I can convert it into a 1024 or 2048, depending on the number of vectors, the dimension of the vector, the amount of information it is held on is changes actually. So you can think about this more like compression type of a thing, I'm compressing information from one dimension to another dimension, so that now the compressed data is in a much smaller dimension, but I could use that for many purpose like searching. So just to give you example, you have taken a 2 images of cat, you have embedded into, let us say 1024 vectors, and you can theoretically compare those cat images to see how close are they. So if you were to compare 2 cat images versus 1 cat image and 1 dog image, you will know that the 2 cat images are much more closer than the cat versus dog, type of a thing. Yeah. So now let us get into a little bit of the architecture. So typically, what does one Gaudi card basically have? So this is, I am talking about Habana Gaudi 3. There is something called Habana Gaudi 2, which was the previous version. So Gaudi 3 has 128 GB of RAM. So this is the, the RAM associated to the GPU or the ASIC card. So one thing you should understand is there is a RAM associated to the CPU, which is what we traditionally talk about, but these are memories associated to the the card itself. Yeah, it's very important, this difference, because you might think if CPUs gives you so much of RAM capacity, why are they not very efficient? Because that's where it differs, because there are RAMs itself very different. So when you talk about DDR RAM versus, this is what is called HBM. So that's called high bandwidth memory, they are extremely fast and they are costly also. So compared to something like DDR 5 or 6, they are much more costly for the same. If I were to take 128 GB on both, there will be an order of magnitude cost involved there, but they are fast also. And then there is an SRAM, which is a smaller portion of it for certain things. And then when it comes to the networking, it allows 200 GB this one into 24 stuff. So it is, and this is PCI slots possible 16, and ROCE is basically when it comes to networking, there are different technologies available. NVIDIA, if you have ever used NVIDIA, it's basically its own NVLink and other things. So here it is RDMA over converged Ethernet. So here if you understand the networking, Ethernet has been there for quite, and most of it is open source. So there is no major proprietary stuff here compared to something like InfiniBand from NVIDIA and stuff, actually, where you have to pay for it actually. But whereas when it comes here, you don't have to pay for it. So that is RDMA over converged Ethernet. That's what ROCE stands for actually. Very important from the proprietary nature of it. And added to that, RDMA basically allows remote memory access actually. Remote direct memory access, it's called. See, typically when the accelerators want data, they need to go through a CPU to access it. But that basically, anytime you go through a CPU, it slows down, and that's where the direct access is possible in cases like this, and then the tensor processing cores and stuff, and matrix multiplication engine. We will see that architecture because predominantly I wanted to cover the hardware side of it so that you understand why it is very fast, and why it is, unlike proprietary architectures, it is much more open compared to its counterparts. I will skip for here. There are some competitive Gen AI pricing stuffs and stuff which you can look at. From a software framework perspective, Habana uses, actually it has a framework of its own called Synapse actually, but most of you don't tend to work with Synapse. You can directly use PyTorch as a deep learning framework and run models on it. But when the model gets deployed, they are basically converted internally. And if you understand it, typically hardware optimization always happens. Whenever you are deploying a model into a CPU versus into a GPU versus into an ASIC, typically there are model conversions and optimizations that happen through just-in-time compilation while deploying this. Yeah, so this is available both on premise. You can have it installed, but they are very costly. As I said, a single system with 8 cards probably can cost anywhere from $200,000 to $300,000, which is probably like if you were to take like $90 per rupees per dollar, you're easily talking like a single system with 8 cards costing like 2.7 crores. That's why a lot of people cannot own it, but they are available in rental forms also. So if you want it only for like 5 hours or 10 hours, you can rent it from either IBM Cloud, Denver Cloud, or the Gaudi 2 is even available in the AWS system per se. So most of these cards, like all the 8 cards, you have a host machine, which is a CPU system with its own RAM. And then you have 8 cards associated with, where each card has a 128 GB of high bandwidth memory, per se. So your CPU RAMs are much higher actually. They will be normally in the range of today's, if you see today's Intel Xeon systems, CPU systems, they have like a 1 terabyte to 2 terabyte type of RAMs possible, with each graphics card or ASICs having its own memory of 128 GB. In this case, it is 8 cards. If you were to have a full system, it is 8 card into 128 GB. So almost like a terabyte of high bandwidth memory also available for the graphics or the accelerator processing. We'll skip here for lack of time actually. So we'll get into little more core. If I were to open up one card, what do I see? Obviously, in most of the deep learning, if you have a lot of matrix multiplication happening actually. So that's what MME, matrix multiplication engine, or GMME, or if you have heard of GEM type of thing, it's a very similar thing. And then you have quite a few matrix multiplication engines available, and then you have the TPCs, which is the processing core, tensor processing cores that are available for you to available with a SRAM, around 96 MB of SRAM available within the card per se. So this is a single card. Like this, 8 cards will be put onto a system, and if you want to build a rack, you can build a rack with multiple systems. We'll take a look at it. And then you can build multiple racks and then connect them also. So it's a scalable architecture, as we discussed, which allows you to connect. So here it's basically PCIe Gen 5. So now probably the next generation will be Gen 6 with more memory and stuff like that. So the capabilities constantly increase. So we can't, and if you look at the, floating point operations, T-flops, which is discussed. So you have different capabilities. So it supports vfloat 16 and FP8. So if you understand, typically neural networks are stored as weights actually. So they are stored as weights. So let us say you have an 8 billion model. If you were to store an 8 billion model with, let us say, FP32 precision, that means FP32 is 4 bytes. So 8 billion model with 4 bytes will convert into 32 GB of memory requirement just for the weights of the model. Computation and other things, it might need more stuff. So whereas if you go into something like bfloat 16, it is a half precision. So data types like bfloat 16, FP16, they are half precisions. So they need only 2 bytes. So the weights are not stored in FP32, whereas the weights are stored in 2 bytes, which corresponds to, in case of an 8 billion parameter model, it corresponds to 8 into 2, which is 16 GB. So the same thing, if you further reduce it into either FP8 or int8, it will be 1 byte, So both FP8 and int8 will consume 1 byte. That means if I were to store the weights, again, either in the FP8 format or the int8 format, 1 byte, 8 billion corresponds to 8 GB. Now you can think models like 670 billion parameter and all. So there are very large models, and now you know the challenges. So because the model doesn't fit into single memory, you need series of machines to fit them actually, either 8 cards, or even sometimes they might not fit even on the 8 cards. You might need multiple systems to even fit them, So now you understand the challenges. So when the model is split into different cards, into different systems, and then inference or training is happening, you can see the insane amount of computation that happens between that. Anybody who has worked on distributed processing understands if you have used frameworks like Spark, when you have large Spark clusters, the bottleneck normally becomes the movement of information or data between these systems or the nodes, So that's why they are predominantly designed with high, networking speeds actually. But nevertheless, it still could be a challenge based on the type of problem you solve. Now, how the cards are coming, you can see here. You can get single accelerated card like this, which is available, or you can get a universal baseboard. So here you can see that it is within the board there are 8 cards which are there. Or now recently the PCI type of things also. This is more like you buy a card and you attach it to your PCI slot type of a thing. You can do that also actually per se. So they are available in 3 different forms. This is mostly used in data center where you have rack-based, rack-based systems where you want to build them per se. This is mostly used in cases where you have more of a local desktop or a server running on a more like a tower-based systems where you can attach them, And it can be also used in data centers, but nevertheless, there are, I would say this might be more simpler in a data center compared to this per se actually. This is the, the cards capability when it comes to teraflops computation. So I will skip for, I think it's a more or less the same thing. And you are just adding all those things together. Now, coming to the networking side of it, So how does these things communicate? So if I have 8 cards in a system, they need to sometimes communicate between them. So let us take a case where I have the 670 billion model. It will not fit into, let us say, if I were to do 670 billion model in FP8 itself, I need 670 GB of memory, not the CPU memory. We are talking in this case, the graphics card memory. So the question comes is, the only option is what is called tensor parallelism, where the models are consisted of layers. What you do is that, let us say if it has 32 layer, let us say the model consists of 32 layers, What you do is you load 4 layers in each graphics card, combining them to 8 into 4, 32 actually, That's how you fit them into a larger case. But if the model is small enough, let us say it was an 8 billion model or a 70 billion model with FP8 precision, that can load into a single card. You don't need to see. This is where you have to understand. Sometimes a small model dispersed into 8 cards might become inefficient also, where actually the bottleneck is not the computation. The bottleneck becomes the communication across the cards per se. So how do you finally deploy matters, because splitting of models is predominantly preferred in larger models. If you can have a model fit into a single card or into 2 cards, let us say if you take a 70 billion parameter model on a bfloat 16 precision, you need 140 gigabytes, which will not fit into 128. So single card will not work. And then there might be an overhead of 50% when you are inferring like activations to be computed and many other things. Or the KV cache in case of transformers and stuff actually, attention stuff, things like that. So you need, probably it will fit into 2 cards actually, in that case actually. But can I do the 70B bfloat 16 into 8 cards? Theoretically, you can do it, nothing wrong, but you have to be very careful. When you split that model like that, now 8 cards needs to communicate. So here, if you see the communication, it follows an all-to-all connection. So there's nothing like centralized here, One card can communicate to another card directly. So there is no head node card type of a thing, It's an all-to-all type of a connection per se. So you can think about the complexity now once we take from a single node into a multi-node cluster, where it becomes all-to-all type of a connection. So I'm not going to go into that. There is quite a few things to understand in terms of how the networking is done and things like that. This only matters to people who use large clusters for either training purpose and things like that. Inference is much more easier. In inference, you don't have to worry about it. You can horizontally scale it actually, yeah. So this is the overall architecture. I'm not like just you have your storage, things like that. And as I said, it is Ethernet based, communication fabric. That's basically there. So host machine will be a typical x86 server like Intel Sapphire Rapids, or it normally will be a two socket system, two socket system with each socket having either 72 cores or 96 cores or higher also actually. It could be a Sapphire Rapids, which is the 4th generation, or could be an Emerald Rapids, which is the 5th generation, or could be a Granite Rapids, which is a 6th generation. So what is the role of a host? Host basically loads the model initially and then sends them to each of the cards. And then the inference or the training really happens in the card. So whenever a communication needs to happen with the host, it will happen. So the offload happens, and then basically the training or inference happens in that, per se actually. So this is a rack level diagram. Same thing. So if you really look at here, let us take a case where here you have 8 compute nodes. So 8 compute nodes, and then how is the 8 coming? Watch out here. So you have 3 here, you have 2 here, you have 3 here. So that forms the 8. Each of the 8 has 8 cards in it, So this is what is called a node. A node comes with you have an x86 CPU architecture with probably a 2-socket system, and then 8 ASIC cards. Architecture wise is very similar to GPU, so no much different, but how the communication happens, and other things differs actually per se. So that is where, and then you have a compute fabric here actually in between that, so that's where you will see 64 Intel Gaudi 3 accelerators. So that is 8 into 8, and then you can have like this multiple stuff. And within a rack, you can have on top wise also actually, if it is like you can have multiple stuff. It depends on the power per se. So just to give you a background, each card consumes around 900 watts. So if you understand your laptop is in the 40 to 60 watt range, typical laptops, unless it's a gaming or something which might be high. So you can see this is per card 900 watts. So that means 8 into 900. So 7.2 kilowatts is the single node's just acceleration power consumption. And if you take the 2 CPU nodes, so the CPU system by itself will be around 500 watts actually, Then cooling, many other things consumes power. So we are talking a single node by itself, we are talking in the range of 9 kilowatts to 12 kilowatts type of a range, depending on how you see that. So you can see how much a rack requires. See, this is where data center design is completely changing a lot with accelerators coming into data centers. And some of the new NVIDIA based cards, if you see, you can't, because these are water cooled. They are not air cooled. I think they can be air cooled also, depending on how you put the placings and stuff. But typically they are water cooled per se. But I think if you have sufficient spacing, they can be air cooled also between nodes and stuff. But with some of the latest that are coming, you can't do that. You need what is called immersion cooling. Actually, you need to put them into a liquid so that the liquid absorbs the heat and then transfers that heat back to that type of a thing. So even in an ASIC, the amount of power is high, but typically they are less than a graphics card, because if you see when you need a 900 watts here for a card, 600 to 900 watts for a card, depending on its capability. In the case of NVIDIA, it can go to 1200 watts or above actually. Yeah. So it all depends. And then networking, all other things also eat some power per se actually. And then you have the storage on the side. Storage Fabric control plane servers, and there are some other management stuff and things like that. So this is how you build a rack by overall combining multiple systems. Performance, there are some, if you want to see the numbers, you can just search for it, model performance data for Intel Gaudi card. These are all open links, so nothing proprietary. Again, the software stack we did discuss. Predominantly, you will tend to work with PyTorch. Again, for quantization and other purpose, if you want to quantize your model from FP16 to FP8 or vFloat 16 to FP8, there are quantization toolkits and stuff that are provided too. And LLM serving integration, you could use softwares like VLLM to serve the system, and then DeepSeed for is also used internally. You don't explicitly have to do anything there. And typically you will tend to work with the PyTorch layer actually. Then there is a graph compilation happening. As I said, when you write a PyTorch code, the model has to be compiled and explicitly optimized for the hardware actually. So this layer, so the same model, if you take it for NVIDIA hardware versus ASIC, there are different compilations that are happening. This is the overall stuff I wanted to cover so that you get, and you can take a look at it, what type of models you can run. There are quite a few. Go to the web page, it tells you that there are quite a few models supported here, both in terms of pure LLM, large language models, and then there are, these are embedding models. This is the Whisper is actually the speech to text, type of model. And then you have visual language models. The Bridge Tower and all is like basically a multi-model actually. It can embed any information, be it text, voice, or image, as I said, if you use something like VLLM and all, you can have Docker-based running, and then through Kubernetes also per se actually. Quite a few things possible with them, just like any graphics card that you use. These are some developer resources and stuff. I will stop here because I think we have. I gave you a hardware overview. Now just let me see if I can show the system per se. I don't know. I think I'm not shared the. I might have to share the window. Just let me unshare and share it back, Or did it get? I hope I'm sharing it, Okay. Are we able to see my screen now with the okay. Yeah, so I'm actually connected to a system. I'd already logged in before that actually. So when you came, typically if you what type of a host it is. So if I do ls CPU on the system, I can see. Okay, so if I were to show you this, so you can see that in this case, it is an Intel Xeon Platinum 8.5. So that means 8 stands for Platinum, 5 stands for actually Emerald Rapid. So it's an Emerald Rapid system. It has 2 sockets. So that's where you see 2 sockets, and cores per socket is 40 actually. So, and they are hyper-threaded. So that's why it is 2 into 40 into 2. So that's where threads per core, and that's where you will see CPUs to be 160. So this is the host machine. Now, what are the accelerator cards? So if you have ever used it like NVIDIA SMI type of command for system management stuff, similarly Habana Gaudi has its own. It is called HL-SMI. So you can see there are 8 cards that are running. So card 0 to card 7. So the normally numbering starts with 0 actually, and then 7. So it's actually running. So there is a workload running for one of the customers. So that's what. So now you can see what type of a current usage. This is the cap. This is to cap is to ensure that you don't burn the card itself, because if you do clocking, hyperclocking type of thing, it can go beyond that. So it's always capped at 900 watts, but you might not use it. See, this is the current usage of the card when it is running, and what type of a memory usage. So it is effectively like utilizing 90%. So and you can see the temperature. This is in a cooled environment. So you can think if you do not have the right cooling and stuff, this temperature can go. So it is average 40 degrees. So it's not, because if you see the data centers are normally kept at 24 degree Celsius. So in spite of them being kept at 24 degrees Celsius, the cards are running at much higher temperature. So you can see that the localized temperature is much higher per se, and it's actually running. So you can see there are Python processes running actually, and out of the 128 GB RAM you have, it is actually utilizing very well. Actually, this is very rare. Actually, you don't normally tend to get 96%, but in this case, it is predominantly using that. If you want more details of a card, also you can do. There are many more things you can do. SMI, HL-SMI. If you do, I think -I0, you can get more details on the card. What type of a HL-SMI version you are running, the driver version, and things like that. I think I will stop here. I could have shown you the entire running of some inferences and stuff also, but nevertheless, it doesn't matter. It is just like any other graphics card per se. So if you have a very large computational problem that is involved in that, you can do that. See, where does ASIC differs from GPU is the fact that, let us say, typically you can run only deep learning type of workload in this type of stuff. You can't run something like a climate simulation, which is using something else where you need FP64 precision. No, the hardware doesn't support that. See, there might be some hardwares which supports high level precision to very low level precisions, but these type of things are specifically designed to work on 2-byte precisions and single byte precisions or lower, so bfloat 16, FP16, most of them sometimes supports FP32 also 4 bytes. But if you are doing something like scientific computation, you might need FP64 precision, these are not well suited for such type of workloads. But a GPU might still be able to do that actually, depending on the type of GPU you are using. Not all GPUs support it, but some of them do support it actually. I will stop here and take any questions that you have, or if you want to go through, the standard question that came up in the, I think I'll have to open my mobile to see that. I did not go through that.
I just do it a little bit, sir.
Yeah.
In the chat box now, I'll just ask for now answer that. First question. We studied 8085, 8086 architecture. How Gaudi architecture in compared with 8085?
I'm not sure. Did we? Because I don't know whether I am getting the noise or there's some So are you asking how the architecture compares with CPU?
No, how it compared with 8085 processor? 8085 processor.
No. 8085 and all is only today used only in colleges for learning purpose. When you say x86, it is 8086. So more than that actually, but. Nevertheless, these type of if you see the entire CPU architecture, you have 3 predominant stuff. So you have x86, which is Intel and AMD type of companies. Then you have ARM. Then you have what is called RISC-V. So you might have all heard of ISRO's chip, which is basically a RISC-V based chip. See, where it differs is that x86 is a proprietary architecture, proprietary instruction set architecture, that's called ISA. So it's predominantly used by Intel and AMD. Whereas when it comes to ARM, anybody can develop in ARM actually. You have to pay the royalty for it. So the graphics cards which you see and stuff most of them are built with ARM type of stuff. And then RISC-V is where the latest. RISC-V is more of an open instruction set architecture, which is called Open ISA. So Vikram processor that you saw, Vikram 32 or something, that is basically a RISC-V. So you don't pay for the royalty of the instruction sets per se, because the instruction set is open, and then you do that. That's how it differs,
Thank you, sir. Thank you for that
I have one question,
answer.
sir. My name is Murali Bhaskaran.
Sure.
Actually, when you design a processor, along with that, we need to develop the instruction set also. So when Gaudi was developed, what type of instruction set they use?
See, it is actually using ARM. So I don't know exactly the instructions that are used actually, but it is following the ARM, because it is actually, even if you see, it is an Intel, processor. Basically, it is actually manufactured in TSMC, Taiwan. It is not. It is not done in Intel's manufacturing process per se. Yeah, it uses ARM actually.
Okay. So while you think of designing Audi processor, so what type of application will run and all they pre-discussed and then they developed, or stage wise still it is developing stages, Gaudi processor?
Yeah, so you will decide. See, typically ASICs, as I said, they are application specific. So when you are running deep learning, the most important thing is the matrix multiplication engine, and then what type of a precision do you want to support? So as I said, these processors do not support something like FP64, which means most of the scientific applications you can't run, because most of the scientific application precision is very important, and you need high precision compute data types like FP64 and things, So and then they are restricted for other reasons also, because again, as I said, the cluster nodes, everything is designed for extreme scale transfer of data back and forth and things like that. Yeah. So when you design itself, you have to design it like that,
Okay.
Yeah.
Whether it will support a multi-core, sir, or it is a single core system, sir? Gaudi.
No. All these systems have thousands and thousands of cores,
Course. Okay. Thank you, sir.
Yeah. So when the TPC I showed you, they are tensor processing cores only actually, Yeah. Typically, if you take even a small GPU, it has something like 5,000 cores,
Okay. Yes, sir.
Sir, very good evening, sir.
Yeah.
My question is, yes, all these advanced chips were fabricated out of Indian geography. Now, with respect to India, how Indian government or people like you, how we are planning to travel in this industry, and where are we right now? How we can enrich our academic strength in this direction?
Okay.
Because now, Trump giving a lot of troublemaking for our R&D, other things, people traveling here and there. So how these things shaping up in India?
Yeah. So to frankly speak, from a manufacturing perspective of processors, we are probably like 2 to 3 decades behind. Somebody like Taiwan. See, we did start the work. I think it was during Indira Gandhi. We had there was some processor unit in Mohali. What happened is it got burned. Nobody knows why. What happened, was it a sabotage or something like that? Nobody knows actually. After that, what happened is none of us took initiatives to get that working. So now the government has started it, but if you see that they are in the range of 180 nanometer, 28 nanometer to 180 nanometer nodes. But most of these high processing systems that are today developed, so if you look at the NVIDIA stuff and all, they are in the range of 4 nanometer, 5 nanometer, max 7 nanometer. So most of them are less than that. So we are already talking 2 nanometer, 1.8 Armstrong and 1.4 Armstrong. So 1.4 Armstrong corresponds to 14, 1.4 14 Armstrong corresponds to 1.4 nanometer. So these type of nodes are the type of machines that are used in building such chips, and the complexity involved is too high that only very few countries have such things. So Taiwan obviously holds, I think, 70% of the market share in what is called, advanced processing nodes. These are called advanced processing nodes. Anything below 5 nanometer technology is considered under that. Actually, very few countries. Intel has a plan, but that scale is still with, I would say, this. And China, I think, up to 7 nanometer they are able to do it. I think we are what process we are making is not for this advanced processing. It is mostly for something like cars, probably TVs, and others, which were you don't need to have this advanced processing. You 28 nanometer to 180 nanometer type of process are still fine, type of a thing. Yeah, we are probably like 1 or 2 decades, because a single fab cost $30 billion. So you can think $30 billion is a single fab's cost. Then the operation cost, the knowledge associated with that. I think that is too high for something like India at present.
So now, yes, I understand this difficulty of money, and it is not easy to invest and make the money out of this. We need different stakeholders. But yes, India, we cannot do everything. But how India is focusing any facility, because IEEE also people talk, and then they finally come up with MEMS-based R&D, and then device, and then prototype, and then entrepreneurial things in this MEMS region, not in the CPU or core Intel kind of stuff. That MEMS is also a very strategic planning, not to go to this kind of below 10 nanometer technology, better focus on 100 micron technology, where something is useful for Indian space, Indian DRDO, like sensing, developing sensors, integrating all those things. But now policy is done, but still Indian private industries hesitant to go kind of Intel kind of things. But Tata comes, and again they are focusing on some strategic industry.
Yes.
Because of stocks involving in it.
Correct.
So
I don't think anybody is focusing on the high end, because you can't get into the high end without getting through the understanding of low end. See, there's a lot of capability involved here, which is, even when you talk about TSMC fabricating it, actually the supply chain is very complex. The machine comes from ASML.
Yes,
the machine comes from ASML. If you understand the entire stuff, see, I would say there are a couple of courses in Purdue University. One is the manufacturing, advanced manufacturing, and then one is the design side of it. I would say if you are really interested, try to attend it. I think one of them is free. Manufacturing one is free, and the design one requires a $20 registration fee. I don't think it's a course fee per se, and you can get a certificate out of it. Once you go through that, you will know the complexity associated here, because when you go into 4 nanometer, 3 nanometer, 2 nanometer node, there's something called yield. Yield is a case where you make 100 chips, out of which, if your yield is 70, that means that 30 chips are actually bad, or they are of lesser processing power, So as you go lower and lower in your manufacturing precision, like, your chances of errors are very high, and that's why even the cost of chips are also very costly, especially if your nanometers are there. Yeah. So I think India has a long way, in my opinion, but at least some good things are happening where we started that. And the government said by 2030 they want to get to the 7 nanometer node, But if you look at Intel and TSMC, they are talking about 1.8 nanometer or 18 Armstrong and 14 Armstrong type of chips, which are very advanced,
Okay, sir. Thank you, sir.
Yeah, sure.
Sir, there is question in the chat box. So this, I think you have answered in the previous question, but still, though there is a huge demand and usage of GPU in India, what are the key reasons for non-availability of domestic GPU manufacturing unit in India?
Yeah, that is the technology complexity, because most of the GPU, if you see that they are in the 4 nanometer node and below. Actually, we don't even have, see, the Tata plant, which is the most advanced, which is set up itself, is only 28 nanometer, So we are far away. It's not easy to move from 28 nanometer to 4 nanometer. Yeah. I think it will take time before we can get to there. As of now, if you want, what you could do is design it in India. A lot of design happens in India. So India is considered little advanced in design of processors, but the manufacturing still happens outside, either in TSMC in Taiwan, or it could be Malaysia. Certain things are manufactured in Malaysia, or it could be US or certain fabs in Europe. So at present we can only design here. The manufacturing will happen outside actually. Yeah.
Next question, sir.
Yeah.
What are the future trends in IT technology?
What are the future trends? Okay. Yeah. See, as I said, the processing technology by itself is changing a lot. See, if you look at all this, we are talking about von Neumann architecture. See, what is the fundamental problem with von Neumann architecture is basically whenever you do computation, you have to move the data from the memory all the way into the cache. And this is not a very, this was fine previously, but now with so much of data, the movement. So if you see, most of the time, the energy is lost in moving the data. Computation wise, probably it is using 30%, 70% is lost in just moving back and forth, So new architectures are slowly evolving. So if you look at the Cerebrus wafer scale, it is actually a very different, it doesn't have a unified memory. It has cores associated memory, cores associated memory, cores associated memory. So it's a little different type of an architecture where processing is faster. So there are some more, as I said, photonics is coming. So the second slide I showed you had quite a few things, Yeah, second slide I showed you had quite a few things which talks about, more like wafer scale engines, photonic stuffs, quantum computing, then certain type of analog computing which could be still used and things like that, Yeah, quite a few things happening. It's a very, very interesting field. And I would say that you should follow some bloggers or LinkedIn person, like, which to understand what's all happening in the processor industry. Yeah.
Thank you, sir. Next question. How does the global IC supply chain impact the industry?
Supply chain,
Yes, sir. IC supply chain.
Yeah, supply chain is very, very complex in this field. See, even if you say whether it is US making the chips or the Taiwan making the chip, at least from what I have read and seen with respect to that, probably 20 to 25 countries are involved in it. As I said, the machine comes from Netherlands, ASML. Then some of the materials and stuffs come from Japan. Then there are certain things come from US. So the supply chains are very, very complex in this type of things. So setting up that supply chain and ensuring that you have everything that you need, including, see, if you see that during this manufacturing, you need water in excess quantity, and that too very pure water, and even making such water itself is a very complex process, because the polishing and stuff, when happens, they use water to do that. You cannot have impurities in them, because when you talk about 4 nanometer, 2 nanometer type of scale, even a small impurity can cause an issue onto the chip actually. So extremely complex. I would say the supply chain is very complex, and you're easily talking about 20 to 30 countries itself involved in making chips in the 2 nanometer and 3 nanometer type of nodes,
Thank you, sir. One last question. How to bring GPU-based architecture into the classroom discussion instead of regular computer organization and architecture?
Yeah, see, most organizations have CUDA as a programming language. See, the problem is hardware by itself. Not every college I've seen has that, but hardware is the first aspect of it. So that can be little bit alleviated if you use Kaggle and all. Kaggle kernel, if you see Kaggle kernel, it is a free and it allows up to 6 hours of GPU compute on a day once you have registered for it, So that's available. CUDA is being taught in many, but what CUDA teaches you is that how to basically use parallel algorithms to solve. If you are solving a 1024 by 1024 matrix, you could convert them into 256 by 256 4 quadrants, get it multiplied at the quadrant level and then assembled back together. So CUDA teaches you that parallel aspect of it. There are many more courses like that actually which teaches you that. So it's already there in the curriculum, but the question is, very few people have access to these large compute clusters and stuff, to solve some complex problems,
Thank you, sir. Thank you for the wonderful question and answer session. So, without further delay, I'll just formally propose the vote of thanks. So, we had today's webinar on Beyond GPU, application-specific ICs and AI, research and deep learning. So, discussing about the various processing units like CPU, GPU, APU, and TPU, tensor processing unit. And he just spoke about the customer challenges with AI computing solutions. So there is it needs more choice and it needs locked in, and it is ability to scale and maximizing the efficiency. So he touched upon all those things, and he also specified about the AI applications and AI functions with focus on multimodal LLM and RAG. And he touched upon the Intel Gaudi AI accelerator overview. And also he just explained about its efficiency, network flexibility and design. So he also specified about the specification and block diagram and also about the cluster architecture. And he specified about the software suite also. So these are some of the things that he discussed, and he also explained with some real syntax of getting that done. And I take this opportunity to thank the speaker for his effortful session, and he just gave a detailed explanation, and also in particular the very pleasant question answer session. Thank you so much, sir. I would like to thank our mentor, Mr. H.R. Mohan, sir, for his continuous support. And I thank all the organizing units for supporting us in organizing this webinars. I take this opportunity to thank all the participants who took effort in joining in YouTube live streaming and also in Google Meet, and be a part of this question session also. And before ending, I just want to list out some of the forthcoming events, forthcoming webinars. So on October 15th, 2025, we have a webinar on Gen AI in improving cloud security. And on October 29th, we have a webinar on computer science education and software craftsmanship. And on November 12th, we have a webinar on hyper-personalization in software-defined vehicles, shift from adaptive ecosystem to identity-driven mobility. So for further query, just log into our website, csachennai.net, and you can just have a view of all the forthcoming webinars. Thank you. And you also have the link in your credentials, what you have received today. You can just even register through those, that also. Thank you. Have a nice day. Thank you all.
Yeah, thank you.
Thank you, Rajeev.
Yeah, thank you. Thank you all. Bye.
Very nice. I think it is mind-boggling, but still, how come Intel is struggling to capture the market with all these things?
Yeah, so NVIDIA has a mover's advantage. So if you really see that they were into GPU for quite some time, actually a lot of people do not understand that Intel is actually older than NVIDIA when it comes to GPU, but it was only doing integrated graphics, it was not doing discrete graphics much actually. They made some wrong choices because they had always the capability to build discrete graphics. But now, if you look at the B60 type of cards, which are which are coming into the market, so they have started slowly getting into that. ASIC is a different function. So ASIC is completely, that is an acquired company. So it was an Israeli company that Intel acquired actually. So still with Intel per se actually, yeah. So I think they are slowly catching up, but I think I would say that they missed the boat for some time,
Correct. See, now they are under the mercy with NVIDIA. Now NVIDIA is investing 5 billion.
Yes, yeah. That does happen actually. So if you see, Apple went through the same thing.
Correct.
Microsoft invested in Apple, but now Apple is as big as Microsoft,
Correct. That's right. But I was wondering, improper decision at one point of time can cost the company so much,
Correct. See, it is very similar to why we lost manufacturing in the chip industry, because when the fire happened, we did not take the initiative to rebuild it,
Rebuild that, yeah.
So if we have rebuilt it, you can think we would have been as advanced as any other country,
Correct.
Yeah, sometimes decisions matters actually. Decision matters, and that backfires,
Correct. Very true. So you have to be in technology industry. You have to be always at space.
Yeah. See, that is what Intel CEO said, that only paranoid will survive,
Correct.
And he has a book also on that, actually, I think.
The same. Yeah, paranoid.
Yeah.
But thank you very much.
Yeah, thank you all. Bye.
Very interesting.
Yeah, thanks.
Thank you.
Bye. Yeah, bye.
Okay. சரி ஆக்சுவலா வேற ஏதாவது இருக்கா?
Can you provide the speaker's LinkedIn ID and Gmail ID?
Okay.